So I have this expression for HAI. Now this expression can be simplified in two ways. One is, of course, I will bring in a better expression for rate of change of vector Ci with respect to I. Better in the sense it will not be having any d dt, rather than it will have some omega and a cross product in that way. Okay, it will not involve any derivative. It will be equivalent to the derivative, but it will not involve derivative. That simplification I am going to do. And the other simplification we can do to this expression is based on the fact that this working coordinate system is comprised of axes which are already known to be the principal axis. Since these the three axes are principal axes, it means that these things are zero already. Right? And the matrix being symmetric, the other three are also zero. Okay, so these double summations, what you are seeing here, can be simplified. It will have very few surviving terms, and those surviving terms I am going to write here. What all we will have? We will have IA11 omega 1 dot E1 right here. My claim is that only few terms will be here, those I am writing. How many terms? 2, 4, 6. Only 6 terms. Whereas here, whatever I had here, there were how many? 18 terms. 18 were there. Now I have only 6 surviving terms. All terms involving IA, IJ, where I is not equal to J will be gone. Okay. So this is the first simplification I have obtained. The next simplification is I am going to get rid of these derivatives here. How do I get rid of these derivatives? Since E1 is embedded this is a result maybe in the third or fourth lecture. If E is a vector fixed in frame M, then the rate of change of that vector with respect to a frame I will be angular velocity of frame with respect to I cross with E1. Call this 1, 2 and 3. Substitute 1, 2 and 3 in star previous slide. This is what I am calling as the star equation. Replace this by omega cross E1, this by omega cross E2, this by omega cross E3. Okay. Now omega mi is I'm going to write this as in my working coordinate system as this. With 1 minus E3, 3 with 1, 3 with 1 gives 2, omega 3, 2. What does this give me? This gives me omega 1 E 1 E2 E3 2 3 2 minus omega 3 E1. 1 and 3 minus E2 and 2, 3 plus E1. Okay. So instead of writing this substitution, writing about this substitution here, I should rather say substitute these three things. It is more processed. Substitute 1, 2 and 3 in star of previous slide. Okay. Substitute this and this. Take these three, go back here and plug in here, here and here. Okay. After this substitution, if we collect coefficients of E1 together, then E2 together and E3 together, we are going to get the final form that I am trying to derive. I'm going to write that expression directly, skipping a few steps which I am sure you can verify yourself. Final form will be IA 1 1 1 2 omega 2 2 2 3 3 3 3. Okay. So this is the rate of change of angular momentum with respect to I. But then according to MESA, with A as valid point, right? So with A as a valid point, the right hand side was simply MA vector, which I chose to write in this new, in the working coordinate system. I had MA1 E1, MA2 E2, MA3 E3. So that is what I am isolating now. So if I call this as 4 and this as 5, 4 and 5 imply, give me 4 and 5 give me 3 scalar equations. What are those 3 scalar equations? MA1 equals right, this is the first scalar equation of MESA, and I call it version 1. Version 1, please remind yourself that by version 1 I mean, what I mean by version 1? By version 1 I mean these 3 conditions are applicable. Point A is a valid point. The 3 axes of the working coordinate system are the P axis, and we are using a working coordinate system which is A, x1, x2, x3. These 3 conditions make what I called version 1. Okay. MA2 is two, three, 3, 3, 1, 2, 3, 2, T, check. All right. Now this is a form with which we would like to start solving a problem if those 3 conditions of version 1 are satisfied. All 3 are scalar equations. Third scalar equation. Version 1. Okay. Now here omega 1, omega 2 and omega 3 are of course the 3 scalar components of the angular velocity vector of the body with respect to I. Recall that omega 1 dot I defined as this, and omega 2 dot was defined as this, and omega 3 dot was a symbol substituting d dt of omega 3. if I have a body M, this is inertial frame I, if A is an arbitrary vector, long time ago we derived a relationship. Okay, for any vector A, any vector A. Now let us choose that vector to be omega mi itself. Okay, then what happens that d dt of omega mi with respect to I is same as d dt of omega mi with respect to m. Why? Because the other term will be 0. Now omega mi I am expressing as this, where E1, E2, E3 are all fixed to m in my coordinate system, right? It means that d by dt of omega mi with respect to m will be what? I will differentiate the right hand side with m, with respect to m. Now potentially this will give me 6 terms. Right? Gives me 6 terms when I am differentiating omega mi with respect to m. But since E1, E2 and E3 are fixed to m, what will happen is that these 3 will not change. Okay, so it means d dt of omega mi with respect to m is right. But then I also have this relationship here. Let me call it as plus relationship. Plus implies that d dt of omega mi with respect to I is equal to with respect to m. It means that omega mi dot, which is nothing but this, a shorter version of this left hand side, is d dt of omega mi with respect to m. But that I have found to be this. Right? So what I am trying to say? What am I trying to say here? what I am trying to say is that in the previous equation, here, here and here, the way to get omega 1, omega 2 and omega 3 is to write the vector, angular velocity vector in your working coordinate system, and those scalar components will become omega 1, omega 2 and omega 3. That is taken care of. The next question is, what will be omega 1 dot, omega 2 dot and omega 3 dot? The answer to that is, you find omega dot mi vector, express that using the working coordinate system. The scalar components appearing therein will be the quantities omega 1 dot, omega 2 dot and omega 3 dot. I would like to write it here. Right now this may look trivial, but when you start solving problems, I hope you will appreciate the way I am explaining it now. That to get omega 1, omega 2, omega 3, express the vector omega mi dot using m fixed coordinate system, E1, x2, E2, x3, E3, and then the scalar components of omega mi along E1 will become omega 1, along E2 will become omega 2, and along E3 will become omega dot 3. This is how you will find these quantities. Take the angular velocity vector, angular acceleration vector, express it in your working coordinate system, and then take coefficient of E1, that will be omega 1 dot. What I am trying to say is that to get omega 1 dot, you need not differentiate omega 1. You need not differentiate omega 2 to get these dot quantities. Rather, if you know omega dot mi, the vector, you express that in the working coordinate system, and then the coefficient of E1 will become omega 1 dot. Coefficient of E2 will become omega 2 dot. Coefficient of E3 will become omega 3 dot. When I solve an example problem later today or in the next class, I will try to highlight the importance of what I am saying now, and I hope at that time you will see how this is useful, this understanding is useful in clearly identifying these omega 1 dot, omega 2 dot and omega 3 dot quantities. Alright. Okay, so with this we are done with the version 1, scalar equations of version 1 of MESA. This boxed equation, yellow boxed equation. Use this as the starting point if the three conditions are applicable. Now let's go to what I call as the version 2 of MESA. Version 2 of MESA. Version 2 of MESA will be useful if the following conditions are being satisfied by the problem that you have in hand. What are those conditions? To begin with, like what we had in version 1, let me go to version 1. 3 conditions I had. Point A is a valid point. That is there in version 2 also. I'm going to write it here. Point A is a valid point. Okay, valid point means it follows one of those conditions that I described here. These. Point A is valid point. Second condition is that the angular velocity of the body is a scalar times unit vector, where the unit vector, that unit vector does not change with I, with respect to I. Does not change with respect to I. So consider a shaft. Okay, consider something like this, which is supported here. Okay, supported at A and B. I guess I have a figure. Let me pull out that figure. This. This is a shaft, right? See, there are supports here. There are supports here. Okay, bearing support. You may recall I talked about such a support, bearing support. And then what we have is a shaft which has such plates attached. So it is a central rod with some plates attached. And what is it doing? It is rotating with an angular velocity omega mi, which can be written as what in this, the way it is, the coordinate systems are shown here. Omega mi is a scalar times E1, and that E1 as observed from a ground fixed observer who is here, ground fixed observer. It's not changing. Rate of change of that vector with respect to I is 0. Right? We are talking about such motion, such a motion of an RV. Omega mi is a scalar times E vector, where that vector E does not change with respect to the ground frame. And note, here I am not saying that d omega dt is 0. I am not saying that. It may be 0, it may not be 0. The scalar part may or may not be 0. But the direction of the angular velocity is definitely not changing. Okay? So this is the second condition. Only when these conditions are applicable, we will use what we are going to derive. Number 3 is the working coordinate system is AX1 E1, X2 E2 and X3 E3, where A is a part of RB. Okay, A is a valid point, A is a part of RB, and the working coordinate system is this. Let's contrast this with the 3 conditions of version 1 so that we have clarity where to use what. Okay, first and the third conditions of version 1 and 2 are the same. In fact, here I should have written A is part of RB. I did not mention that. It is. A is part of RB. Point A is a valid point and is fixed to RB. We are using this coordinate system. The real difference between version 1 and version 2 is here. In version 1, I am saying that the 3 axes are the P axis of the RB at point A. Okay, whereas here in version 2, I am replacing that condition. I am replacing that condition by another condition. So the axis, the 3 axis may or may not be the P axis. I don't care. But omega mi should be omega scalar times E hat, where E hat does not change its direction. I will write here in parenthesis x1 E1, x2 E2, x3 E3 may or may not be P axis. I don't know. May not be. We are not imposing this condition. In some cases it may be. Besides 1, 2, 3, there may be more simplifications possible, but that's not part of what I call as version 2. Alright, so now let's derive how MESA simplifies to this condition. Scalar version of MESA V2. Frame I, body, point A fixed on RB, x1 E1, x2 E2, x3 E3. Okay. Fixed to RB, A is a valid point. Just writing it here to remind ourselves, but this commitment I had made earlier itself, that our working coordinate system will be fixed to the RB, which means A is fixed to the RB and the 3 unit vectors are also fixed to the RB. Okay. So now the MESA would look like MA minus M RCA AAI, which is gone because A is a valid point. Okay. MA we will be able to write as okay. As far as this is concerned, two groups of terms as before. Right? Two groups of terms. But then here I am going to orient my axis in a way such that omega mi is along E3. I can always do that. Essentially, I am saying that I have made E hat same as E3. I can always do that. So this omega mi is like the body is rotating like this. Okay. Omega mi is parallel to E hat, and E hat is itself parallel to E3. If that is the case, then many terms will vanish in these two. So right now I have 9 terms here and 9 terms here, but many will vanish because omega mi is just omega E3, which means omega 1 is 0, omega 2 is 0, and omega 3 is simply omega. So wherever j becomes 1, nothing will survive. Wherever j becomes 2, nothing will survive. Only when j becomes 3, you will have non-zero terms. And also note that this is about omega 1, omega 2 and omega 3. What will be omega mi for this body? It will be d dt of omega mi, which is d dt of omega times E3, which is omega dot E3 plus omega d E3 dt I, which is 0. This is a given condition. So omega dot mi is simply omega dot E3. What does it mean? Omega dot mi implies that omega 1 dot is 0, omega 2 dot is 0, and omega 3 dot is simply omega dot. So this double summation, call it double star, this double star equation will simplify to so instead of 18 terms, we will have only 6 terms. Verify. Three terms will come from this bunch of 9 terms here. 9 will become 3. Another 9 which we have here will again give only 3 non-zero terms, and thus you have only 6 surviving terms. Okay. Further, d(E1) dt with respect to I will be omega mi crossed with E1. E1 is fixed to m. E1 is fixed to m. Omega mi is simply E3, omega times E3. This becomes 3(1) omega times E2. That takes care of this. Into becomes minus omega E1 and dE3 dt becomes 0. Call it 6, 7 and 8. Let me call this equation as 3 stars. I'm going to substitute 6, 7 and 8 in 3 stars. Right? dE1 dt goes here, dE2 dt goes here, dE3 dt goes here. And then I will separate coefficients of E1, E2 and E3. We already have some coefficients of E1, E2 and E3 here. Some coefficients will come from here, here and here after I substitute 6, 7 and 8. The final form what I get for rate of change of angular momentum is this. You get IA13 omega dot minus IA23 omega square E1. Third term is IA33 omega dot E3. Verify. I've said this many times in my course earlier also. These derivations right now you are observing. Go and read it once, my derivation, and then at least once you should derive it. Then only you will be able to feel comfortable with these equations. Going to end the class in a couple of minutes. Just complete this derivation. Okay. Now match this with MA equals MA1 E1, MA2 E2, and MA3 E3, which is MESA with A as a valid point. This gives me three scalar equations. MA1 will be equal to this. MA2 will be again, these equations you don't have to memorize. I will give this on the formula sheet for your exams, but have a clear understanding of how it has been derived and how it will be used. How it will be used we will address in the next lectures. But yes, how it has been derived and what are the meanings of various symbols. First scalar equation of MESA version 2. Second scalar equation of MESA version 2. Third scalar equation of MESA version 2. Alright. Okay, I box it. This derivation is also completed. Alright, we stop here.